Good morning. Thanks for waking up bright and early to come and hear about Binder Zero Day. As he said, my name is Maddie Stone, and I'm currently a security researcher on Google's Project Zero, where my focus is on what can we learn, what can we find out, and things from zero days that are used in the wild, and thus how can we use that information to make zero day hard. Before that, I was on the Google's Android security team. But this is a story of how I found an Android zero day that was being used in the wild, attributed to NSO. So let's go back in time to late summer 2019. This was just at the cusp of when I was switching from the Android security team to move on to Google Project Zero. And I get this meeting invite, not really sure what it's about, show up. There's a lot of people from a couple of different teams within Google, and we receive information saying, hey, we've heard that NSO has a 0 day for Android, and they're using this to install Pegasus spyware on target devices. What do y'all know about it? We're all sort of looking back and forth at each other like, do you have any other details? We haven't heard about this. What's going on? And so this talk will be a story of how I found it, what information we got, what the bug is, how do you exploit it, what does a POC look like, and then what is all this information about in the wild, and what can we learn from it, how should we move forward? So this was my starter project for Google Project Zero. Came into this with no really kernel knowledge, and so hopefully that's interesting, helpful, but our starting point was a bunch of different facts, sort of marketing details about, hey, you can trust us, this capability exists because here's a bunch of different information about it. So one of the first details about this capability was it's a kernel privilege escalation using a use after free vulnerability, and it's reachable from inside the Chrome sandbox. So from this, it already scopes down what we're looking for. We're not looking at Android app space. We're not looking at the framework for Android. We can focus just on the kernel, and we know it's a use after free vulnerability. Next, we heard it affects Pixel 1 and 2, but does not affect the Pixel 3 and 3a. Remember, this was before the Pixel 4 was released. And this is especially interesting. Your first gut instinct is cool, simple. All we got to do is diff Pixel 2 and Pixel 3. Turns out there's a lot more changes than you'd expect because they're running off of different kernels. Pixel 2 is built on the Linux 4.4, where Pixel 3 is built on the Linux 4.9. But the other interesting fact is that we heard it's been patched in the Linux kernel greater than or equal to 4.14 without a CVE. So the without a CVE is not that crazy, because if you've worked with the Linux kernel before, they treat a bug as a bug. It's not a bug is not a security bug, it's just a bug. So they often patch security issues without CVEs. But what is highlighted is that we know Pixel 3 is not affected. Pixel 3 runs on 4.9, but now we're being told it wasn't patched in the Linux kernel 4.9, only in greater than or 4.14. So these are all just details to start putting in our head of how do we narrow it down to which patch for a bug is this vulnerability we're hunting for. So now we get into the technical details about this bug and how we begin to really think of what is it. So the kernel flag option config debug list breaks the primitive we're using. So next step, how does behavior change when config debug list is enabled versus disabled? So thankfully, it's pretty well scoped. There's only 2 actions you can perform whose behavior would change when this flag is enabled: adding to a doubly linked list and deleting from a doubly linked list. And that means that only 3 functions differ. List add has slightly different behavior, and then list del entry only exists when config debug list is enabled, and list del, the parent to that function, either calls list del entry or not. So now we know that we are looking for a use after free, and when you're using that use after free, you're probably calling list add or list del on that freed thing. And so here's an example of what list_del entry looks like. If config debug list is not enabled, then you actually only call list_del. It never calls this list_del entry. However, when config debug list is enabled, we have all of these extra checks enabled, which can end up with a bug on. And these different checks would prevent an unlinking primitive, because they're checking that, hey, the entry we want to delete, does its nexts prev point back to entry as you would expect in a doubly linked list? And those types of checks to ensure that you can't use the unlinking. So this confirms even more, okay, we probably want an unlinking primitive with this bug. The next detail we had is that config ARM64 UAO hinders exploitation. It doesn't break it, it just hinders it. So UAO is user access, basically what it means is that if we were trying to overwrite the address limit, which we are, which tells you whether or not your user mode operation, for example, can access kernel memory or not, it's that bound. Rather than our exploit just overwriting the address limit in the task struct, it would have to change another flag if config ARM64 UAL is also enabled. So we can get from that the exploit is likely using memory corruption to change that address limit. Next, we heard the vulnerability is exploitable in Chrome's renderer processes under Android's isolated app SE Linux domain. So this is very similar to the first bullet point, and what we double checked is that this would actually be true of also Firefox or others that were running similar, but it's likely that this local privilege escalation bug that we're looking for is paired with a browser renderer or Chrome renderer exploit, so that no longer is it a local privilege escalation, it's a chain that can be delivered remotely. Next, the exploit requires little or no per device customization, which again goes back to the kernel thing, but it's telling us that this is likely in the common kernel of Android rather than a OEM customization, such as Samsung's customizations to the kernel or Google Pixel's customizations to the kernel. So it further helps us understand where are we looking for a bug. And lastly, we had a list of affected devices. The last slide of this, I will link to a blog post about this, as well as the P0 issue tracker, and so that's where you can find the full list. So what do I do with this information? Again, as I said, I hadn't looked at the kernels before. Thankfully, had a team with a lot of expertise, but it's just tedious. I started going through patch diffing and I started going through change logs in different patches, using lore to look up for patches that included list_del or list add information. And honestly, didn't find much with this first process. With just these details and my limited knowledge about that space, I had found a bug that I got really excited about, kept following through, and then it turned out that it didn't match every detail exactly. And so thankfully, about a week or two after I had found that bug and gotten pretty discouraged, didn't know where else to look, I'd gotten information that, did you look in detail at Binder? So Binder driver is drivers Android binder.c. And so once it was scoped down to a single file, that's when I began to do the diffing between Pixel 2 and Pixel 3. And there were only actually a couple of significant diffs or changes between those two. They're enough that you could go through every single one of them. And this commit in particular stood out because one, it says use after free in its changelog and that it's fixing it. Next, it's a patch coming from Linux upstream into the Android kernel for Pixel 3. The upstream patch was also only applied to 4.14 kernel. And lastly, the use after free includes a list_del operation on the freed object. So this stood out super obvious when you're patch diffing and thus ended up being the bug. When I went through each of these different details we knew, it ended up matching exactly. So what is the bug? It's covered under the CVE number now. but it is a use after free in the Android binder driver due to a poll handler using a wait queue that is not tied to the lifetime of the file. So what that means is, one, we have a use after free in the Android binder driver. If you're not up to speed on Android binder, it is the interprocess communication mechanism within Android. And so it's a kernel driver, and kernel drivers perform file operations to perform the different things. So in this case, it's the poll operation. And this Android binder driver's poll handler is getting past a wait queue that can be freed prior to the Android binder driver being released. So that is, in a sentence, what this vulnerability is. So this is the binder thread struct. And in the binder thread struct is where this wait queue lives that we are passing to the poll handler and can be freed. And this wait queue has this structure definition where it's just a spin lock and a list head. The list head, if you're not familiar with the Linux kernel, it has a next and a prev member within it. And so if this binder thread is freed, so is the wait queue, because if you notice it's embedded in there, it's not a pointer. But then when we take a look at our poll function within the binder driver, when the file that this operation is being performed on is the binder proc struct, as shown by the file pointer and what it is there. But when then we call poll wait, we're passing that same binder proc as the file pointer, but the second argument, which is our wait queue, is binder thread. So the normal operation that would be secure is that the wait queue that you pass here can't be freed and is assured to be alive until release is called on that file. However, as we've seen, that's not the case here. So taking a step back, as I've said before, I was not the first one to find this bug. It had been patched first in February 2018. After being discovered by syscaller, which is a sysbot, is a fuzzer that is running constantly over the Linux kernel, had reported it in November 2017. So February 2018, after they'd gotten the bug report, had looked at it, they then patched it upstream in 4.1.4, and also the patch had been taken in the Android common kernels for 4.9, which is the Pixel 3, 4.4, which is Pixel 2, and the other devices that were launched in that fall 2017 period, and then 3.18, which is the same life cycle Pixel 1. However, it was never included in the Android security bulletin. So what this means is that OEMs and Android devices were never said, hey, here's a patch for a security issue. You need to now apply this to the devices. So that's how Pixel 3 ended up not being affected. Because Pixel 3 launched in fall of 2018, this patch had been applied in February 2018 to the 4.9 kernel. So it was only affecting all the devices that had been launched prior to that. But there's been some discussion as throughout this one that, is this a 0-day? Should this be called a 677-day? Where is it? And I think that's a lot of interesting discussion for us to have as a community because they have different implications. But I don't think there's one right answer. Because in terms of 0-day, if we consider 0 days as something that defenders don't know about and users don't know about, this is it. Because the defenders or Android or OEMs didn't know this was a security bug that they should have in there. But if we call it a 0-day, then it's alleviating some responsibility of monitoring upstream patches, syncing to upstream patches, and things like that. And instead, this has been left unpatched for 677 days, even though it was upstream. So I think it's an interesting discussion and requires some nuance, but there's also no real one answer, I don't think. So let's get into the fun stuff. How do we exploit it? So syscaller back in November 2017 actually was able to, on its own, create a C reproducer for the bug. So what this is that you see we're opening binder, as one does for a driver, and then we're associating it with epoll. But then we free that binder thread struct with the ioctl binder thread exit. So as of now, that wait queue is still associated with the poll handler in epoll. And then when we exit main as the next step, epoll CTL del is automatically called with an exit, which tries to remove our wait queue from the poll handler. That wait queue has already been freed, though. So now we're performing this list del operation on this already freed wait queue, and that's how this crash POC works. So we have a crash POC. How do we exploit it? Oop. So I teamed up with Jan Horn to write this. As soon as we verified the bug, we reported to Android under 7-day deadline, and we really wanted to show that this was an exploitable POC being used in the wild, and so we got to work trying to write this in less than 7 days. And our goal was to use this bug to grab arbitrary kernel read and write from an unprivileged application context. So the primitive we were using, as I've said a couple of times, is the unlinking of the doubly linked list. And to actually get that arbitrary kernel read and write, we're going to trigger our use after free twice. The first time, we're going to use the use after free to be able to read out the test struct address from the kernel. Because our goal to get that arbitrary kernel read and write is to overwrite the address limit, and the address limit lives within the test struct. So we leak that address the first time, and then we trigger the use after free a second time. And that's when we actually overwrite the address limit. So the address limit is a value which defines the address range that can be accessed when dereferencing user space pointers. So if we change that, then we in our user mode, user space process can now access kernel memory. The timer says I have 43 minutes and I was only a 30-minute slot. But if someone can help me do timing. But so the way that we're going to do this is we're going to actually use vectored I/O, also known as scatter-gather I/O. And so Dishan does this in a similar method he talks about in his Code Blue 2017 talk, so I suggest that talk too if you're interested in this exploitation method. So what is vectored I/O? We are using it because we need a way to reallocate something we control over that now freed binder thread struct. And so the way vectored I/O works, very briefly, is that a vectored read, you're taking data from a source, it could be a socket, a pipe, etc. We're using a file, and we will scatter it to disparate buffers in memory. And those disparate buffers are stated by a certain struct, which we'll get to. Vector writes, on the other hand, are taking data from disparate buffers and putting them into a data sink, in our case, a file. So although vectored reads and vectored writes, in our situation and how we're trying to read and write to kernel, they're actually the opposite. We use the read to do a kernel write, and we use the vectored write to do a kernel read. So I mentioned that this includes different buffers throughout memory. So the struct we're actually using to reallocate the space from the binder thread struct that was freed is an array of IOVEC structs. This array tells these read and write operations where all these different buffers that I'm using, that I'm going to use for these different IO ops. So the struct IOVEC is 16 bytes first, with a pointer to the beginning of the first buffer, and then the second one is the length of what that buffer is. So we create an array of these different structs that is almost the exact same size of our binder thread. Because it is 16 and our binder thread struct was hex 408, we're 8 bytes off. But because the kernel memory allocator basically allocates based on sides and slabs, it was enough that we can reliably reallocate into that space. And so what's interesting is although we're creating these IOVEC arrays in user space, the operations will actually copy them into the kernel. So that's how we get this overwrite of the freed memory in the kernel. So this is what it looks like when we reallocate. We have our binder thread struct. At offset AO is where our wait queue begins, starting with the spin lock and then the 2 entries in the task list. And so when we reallocate our IOVEC array there, then that ends up being index 10 IOVEC, the IOV base, again, the address of the buffer, then the length, and then the next entry, which is another entry to the buffer. And so to overwrite these now, we use our unlinking primitive. Oh, jumped ahead a little bit. So to get to the unlinking primitive, we call EP control del, which will then call EP remove, which will then call EP remove wait queue. So when the system still believes that the wait queue is living in this memory, it is going to try and remove it and do all of these different steps to end up at our list del. And so as of now, when it's trying to do this list del, it wants to delete this entry in the kernel, which points back to the list head. The list head, which is in our binder thread struct within the wait queue. And so we've overwritten those values with using our IOVec array so that now prev in our doubly linked list currently is dead beef, and we set the length to 1,000. So when we perform a list del on this and config debug list is not enabled, so it's not double checking that that list head prev actually points back to the entry as you would expect in a doubly linked list, we now have this structure where it's now pointing prev back to the list head, which is the address in kernel memory. And so now we have an IOVec array where we are saying a buffer is living in kernel memory after they've done the double checks that our buffers were only in user mode space. So this is now how we are able to perform I/O operations to and from kernel memory. So demo, and now I pray to the demo gods. What, not everyone uses a pink terminal? So here I have a, oh, okay. So I have a Pixel 2 device, and if we want to see what the build fingerprint is, oops. So it's running Android 10 in the September SPL, which was right before they patched this bug. And if you look, because we are demonstrating the kernel rewrite by overwriting the kernel name, so here's a normal one. And who am I? I'm just running a shell. We did demo in our Project Zero issue showing as a untrusted app, but trying to video the phone wouldn't have been a great experience. So now I'm going to run our POC, which was released in the Project Zero issue tracker. So it did the first step where we were doing the read to leak the task struct address, which is current pointers equal equal. That's what the task struct address was. We then run this whole thing again where we actually rewrite that kernel address, and we use that ability to read write to now show that we were able to overwrite the kernel name to exploited kernel. So that is how we got arbitrary kernel read write. So yeah, all that's been released. There's a blog post that talks about that super more in depth, as well as others have now put that all together to create a root that is available too if you're looking to root your device. But this led to some interesting conversations beyond just, here's a bug, here's a vulnerability, it's exploitable. There was the whole other layer of this is being used against people. And our job as security professionals is trying to help people. So we reported under a 7-day disclosure deadline, but we didn't have an exploit sample to demonstrate, look here, this is the proof that this is being used to try and exploit people. And the reason why I and others didn't think it was necessary is that it seemed like there was enough evidence that this was being used to target people, and that this fell into Google's published policy of each day an actively exploited vulnerability remains undisclosed to the public and unpatched, more devices or accounts can be compromised. But it did, and it led to a lot of discussions within ourselves of what is the bar for reporting something as in the wild and thus under a very short timeline. How do we all make those decisions that can be agreed to, that we feel good about, that we know we're not just putting this really tough deadline on people? But we decided to do that because there was all these details about this capability with this association to an organization. And also, when I reviewed all these kernel patches, there was only one bug, this bug matched every single detail we received, including the long list of affected devices and not affected devices, and it was the only bug that matched all of these. So after matching it, I went through every other diff within the binder changes, and none of the others matched. But my whole role here is trying to see how do we make 0 day hard by learning as much as we can, and how do we approach 0 days in the wild. And so this has included a lot of different efforts. One, reversing exploit samples. Two, one of the biggest things we've been doing is root cause analysis on the vulnerability. There's often a lot of talk about the exploit payloads and the threat actors behind them, but what is that vulnerability that makes it a 0 day? And thus dangerous. So hopefully we'll be publishing a lot of those RCAs we've been working on in the coming months or so. We've been doing a lot of variant analysis, which the next slide will talk about the variant analysis on this bug, because if we think about it as researchers, we often find more than one bug at a time. You might choose to only exploit one because it's the easiest, but you usually find a couple of other things as you're looking. And so we can assume that the other side is also doing that as well. So if there has been this failure case where a 0 day in the wild has been detected, which is a failure case, how can we make sure that we use every piece of information that is leaked from that detection and that failure to make it that much harder and raise the investment for anyone who wants to use them in the wild? We've also been taking this information to brainstorm new detection methods and work with people in that way. But what this requires and what we all need to be doing is collaboration. So if you want to talk to me after this, I'd love to talk to you to see how we can all work together in this space. But, and that all goes into, obviously, did some variant analysis on this bug to see what else might that have found. Is there any vulnerabilities available that they could plug and play once this one is burned? And so I did 2 different variant analysis approaches. And I went into this case study in depth last week at Blue Hat IL, as well as some other 0 days in the wild. So if this is what you're interested in, that video should be out soon. But I approached it from both what bugs have been patched in the upstream that haven't made it down to the Android devices that were previously launched, as well as are there any other drivers in the Linux kernel whose poll handler uses a wait queue that can be freed prior to that file being released? And so approach number 1 led to a bug that was patched in last month's, or February, last week's Android security bulletin, and it is actually a bug that was introduced by the patch for this first bug and also had been in the Linux kernel. So that's one, I talk about it again last week at Blue Hat. And the second one, I went through 200 and something different files that included calls to poll wait. And thankfully, there was only one other potential bug where the wait queue that was being passed to poll wait was not tied to the lifetime of the file, but that driver is not really used anymore. So it seems pretty good in that respect. But in conclusion, there's a few takeaways I hope you come from this, is that we can use leads even without exploit samples to help find bugs and get security vulnerabilities patched. So I think we all need to always continue to be creative in how do we use information, even if it's not the information we really, really want. Like an exploit sample is always great, but what else can we do? Next is, and I don't have to tell most of y'all in here, but the patch gap, y'all. If you are working on downstream from an upstream Linux kernel or something like that, that patch gap is leaving a super ripe area for exploitation. Just last year, or a few months ago, there were a lot of different pwn2own bugs that were on browsers where those bugs had actually been patched upstream in Chromium. These types of things are continually affecting user and devices, and so we got to get better at addressing that patch gap. And lastly, I'm really ramping up the 0-day in the wild work. I know there's a lot of different people who've been working on different sections of this problem, from threat intel, from exploit payload, from vulnerability analysis. Definitely open to collaboration, so please reach out. And lastly, this was super quick talk. Hopefully you found it valuable and interesting, but if you want more, there's a super detailed blog post as well as information in this POC code if you want to look at it in our issue tracker. And with that, thank you so much.